which can't stop switching all the day. So Harald Welte and Steve Markgraf are going to show you what or other awesome things you can do with GSM. Please have a great welcome.
I'm sort of waiting for my screen to show up there on the screen. I'm not sure if anyone can do something about that. Thank you. Okay, well, thanks for the introduction. Thanks for the welcome. I'm Harald Welte. Over there is Steve Markgraf. We're going to talk about osmocombb, which is a project that's not even 1 year old, but has already managed to, create quite a lot of results. It's about running your own GSM stack on a mobile telephone. Now, I'm going to go through a bit of a, conceptual introduction. By the way, if you've been to this presentation or to my presentation about the same subject at DeepSec or a different event, it's not really going to be that different. So, to introduce about GSM and 3G protocol security, there's some observations that I want to share. Mostly that both the GSM and TCP/IP protocol specs are as publicly available as the other one. So there's no difference in availability of public information. And if you look at the Internet protocol stack, and I mean, when I say Internet protocol stack, I mean Ethernet, Wi-Fi, TCP/IP, and so on, they receive a lot of scrutiny from the academic community, from the independent hacker community, from whoever. Everyone looks at those kind of protocol security issues for, 10 years, 15 years now at least. GSM networks are as widely deployed as the Internet. If you look at the user base, number of subscribers, we're talking about billions of I think 3 billion is what the GSMA claims these days. But the GSM and 3G protocols don't receive that amount of scrutiny. They don't get the amount of research, despite the fact they're widely deployed networks, the specifications are open. And there are a couple of reasons for that, and that's what I want to talk about for a minute or two. The GSM industry is extremely closed, and I frankly have to add it's closed-minded as well. There are only very, very few closed-source protocol stack implementations that exist. 4 might be too low a number, but if it's 4 or 6, doesn't really make a big difference. My point is it's a small number. The chipset manufacturers that produce baseband chipsets that are used in mobile telephones never release hardware documentation publicly. They even only release it in a very limited fashion to the actual cell phone manufacturers. And it's a very closed club. If we look at the handset manufacturing side, the companies that manufacture these devices, we have, first of all, before we get into device manufacturing, we have to look at the chipset manufacturing. The companies that produce the baseband chipsets that are in those telephones, and there are only very few companies that build those baseband chipsets today. It's once again, I would say, a number about 6. And those companies, they license an operating system kernel from somewhere else. They often license or used to license a GSM protocol stack from somewhere else. And only very few handset manufacturers are large enough to be a member of the club and to become a customer of them. It's not like any other electronic component where you just go to DigiKey and you order it, or you go to your favorite semiconductor distributor and you buy a couple of thousand, 100 or 10 or whatever is the amount you want. Right? It's not like this. The cell phone baseband industry, if you ever find any public documentation about those chipsets at all, on the websites of the companies that manufacture them, it always says asterisk, and asterisk in the footnote says, this product is for large selected customers who produce large volumes of handsets only. So you have to be one of the select customers to even get access to the technology. So there are, a couple of dozen companies, if at all, that are large enough that drive the millions of units of quantity that they can actually become a customer of those companies. If we look at the network manufacturing side, it's very much the same situation. This is not really the subject of this talk. I just want to outline this. The network equipment, the cell towers, the back-end equipment, the core GSM network, and so on, there's only Ericsson, Nokia, Siemens, Alcatel-Lucent, and Huawei, and a couple of other smaller ones. And only operators buy equipment from them. And the prices are extremely high since the quantities are low, and it's professional grade equipment, and professional grade equipment always has to cost 10 times at least the amount. So if we look at the GSM and generally the cellular operators, it's also a very unfortunate situation. Now, some operators may take this as an insult. I apologize for that, but it really is that operators, at least many operators, are banks and marketing departments today. Operators outsource not only the network planning, the network deployment, and the network servicing, but they also outsource the network billing. So what else is there to remain, right? It's marketing, it's sales, and it's finance. And the operators mostly only know the closed equipment as it is shipped by the manufacturer. Their staff gets some training in how to configure it, how to put it there, how to set it up, how to make it work, but they have very limited understanding of how it actually works. And if you talk to some operators, then you will hear, yeah, 10 years ago we still got the full source code from Ericsson and we could see what's actually going on, but these days they don't give it to us anymore. This is the kind of stories you hear from those few people at operators who actually would go down to the lower protocol layers. Now, the security implications of all of this is that we have very few people who actually understand the protocol stack outside the manufacturers of the baseband processes and the network equipment. There's relatively limited protocol level research. If you find research, it's related on the cryptographic side. It's on application level, like mobile malware and so on. It's all important research, but it's on a different level than the kind of stuff that I happen to be interested in. And before osmocombb and OpenBSC and OpenBTS and the projects that have been started in the last 2 years, we didn't have any open source protocol implementations, which I believe are key to make people able to learn more about this. There's no point for any student to just read a textbook about GSM protocols. I mean, there are not even any good textbooks for that, as a start. But even if you want to read those textbooks, you cannot make any practical exercises. You cannot go to a lab. You cannot test what you've been reading about, unlike the internet. And this is really the reason why the internet has received so much analysis, so much innovation, so much scrutiny, God knows what. And the GSM world is this closed user group. Now, if you want to look more at the protocols, how do you get started? You can start on the network side. This has been done by OpenBSC and OpenBTS in the last couple of years. I'm not going to talk about this. This has been done. And in January last year, I decided to take off 3 months in order to get started on actually doing the telephone side protocol stack. GSM is very asymmetric on the air interface and on any other interface. So if you run a network equipment, then you can exchange data with phones. And if you run a telephone, then you can exchange data with the network. But you can never exchange data directly from phones or directly from one BTS to another BTS in the actual fixed network. So it's very asymmetric. So if you want to send arbitrary packets to networks, to BTSs, base station controllers, all the actual network operator equipment, what you need is sort of the Wi-Fi card or the Ethernet card of GSM, where, like on the internet, you have a very stupid transceiver that implements the physical layer, the MAC layer, and all the IP packets and every bit in the IP header and the TCP header and so on, you can define yourself, you can modify, you can handcraft, strange packets. You can see how systems react to that. In GSM, so far, this has not been possible, at least not using publicly available equipment. And this is why we started osmocombb. There have been some other projects that tried to do this that have failed. There was a TSM30 project in the past, and there was MadOS. They both got very far, but they never actually got to the point where their own code could run and could drive the full telephone hardware and could actually interact with the telephone network. So bootstrapping processes, you read about GSM specifications, you start to grow knowledge about the protocols, and so on. You try to get protocol traces and you start to work from there. Since we've been doing the network side GSM stack with OpenBSC in the past, of course we already had a lot of experience. Now we only needed to implement the other part. This is just a rough overview of how a GSM network works, just to get this back into your memory. You may have seen this before. What we are talking about here is the air interface. That's the interface between the telephone and the BTS. And now we want to run a telephone where every aspect of the air interface, of the physical layer, of the medium access layer, of the higher layers, are entirely controlled and defined by open source software, so we can modify the timing of the signals, the power of the signals. We want to modify every bit of the signal, everything. And that's why we want to own the baseband here and run our custom code on this phone so we can generate signals towards the BTS, which then gets forwarded into the actual core network of GSM. Not going to go into the details here. This is just, if you read the slides, so you get explanations for the acronyms, what those are. Now, what kind of protocols do we have? Yeah, we have to go through this quickly. You want to see an extensive demo, don't you? So, we have a protocol stack that is defined by a couple of layers. First of all, there's the radio layer. It's specified in GSM technical specification TS 04.04. If you Google for GSM TS 04.04, you will get the very specification that we're talking about. So this is, again, the pointers if you want to read more. On top of the radio layer, we have the LabDM, which is a ISDN-derived layer 2 protocol. And on layer 3, we have sub-layers that are called radio resource mobility management and call control. And then there is sort of stuff that's not really defined as a layer, but there are more layers without a defined number for USSD, SMS, location services, and so on. In order to, look at the various security problems that have been described in theory, in order to practically implement them, we now need to implement the protocol stack, and we need to implement drivers on the actual hardware to run that code. The couple of interesting security problems that have been widely spoken about is, well, there's no mutual authentication. We know that by now. That leads to IMSI catchers. It leads to man-in-the-middle attacks, rogue base station attacks, whatever you might call them. Weak encryption algorithms. We've been hearing all about this. We know encryption is optional. We know there is denial of service against the random access channel, which has first been publicized by our co-developer Dieter Spar in late 2009. We also know there's the radio resource location protocol that allows the network to obtain GPS fixes of the handset without any information to the user. There are all kinds of issues in GSM regarding security and privacy. Now, what we need to do is we need to control the baseband processor in the telephone. If you don't know much about how modern telephones work, then let me just say the baseband processor is not what you run your Android on, or your Windows Mobile, or your Symbian, or well, Symbian maybe in some cases. But in smartphones, you typically have two processors. One of them is the application processor that runs the user interface and you know, all the high-level stuff. Then you have the baseband processor, which is completely independent or not so independent. But it's a separate processor running a separate operating system, running a separate code base. This is the processor we're talking about. So what is this processor? We typically see ARM7 or ARM9 cores in the low-end phones that we are looking at, and the GSM as a first step. It's ARM7 cores. They run some real-time operating system. Sometimes actually they don't run any operating system because it's not required to have an operating system for the kind of tasks it does. We very often, or well, at least on an ARM7 core, it's very clear that you have no memory protection between tasks because, well, an ARM7 doesn't have a memory management unit. There are no virtual addresses. There's nothing. Then next to the ARM core, you have a DSP. The actual DSP model and type depends on the vendor of the baseband chipset. The DSP runs the signal processing part for the RF layer 1. It's only the signal processing part. Don't think that the DSP runs the entire layer 1. That's a wrong assumption. So the DSP really only does signal processing, and it's triggered by the ARM. So the ARM core is the master, DSP is sort of an acceleration slave in the device. The software stack, well, is written in C and assembly, lacks modern security features, most of the time at least, Philipp Weinmann has already spoken about this yesterday, what kind of things you can do with this. Now, the GSM baseband chipset that we're looking at in the osmocombb project is looking like this. This is just a very high-level overview. We have a digital baseband processor on the left-hand side, contains the DSP, contains the ARM core, contains some static RAM, some mask ROM, UART, SPI, the typical microcontroller peripherals, right? It's like any random ARM7 microcontroller with a couple of GSM-specific peripherals inside. Next to that, we have the analog baseband, the ABB, which contains the analog digital converter, digital analog converter, to actually interface between the digital domain on the left-hand side and the analog domain on the right-hand side. Here we have the RF transceiver, mixer, VCO, PLL. That's the device that converts the analog baseband signal that we have here. It converts it up into the respective frequency bands for GSM 900 megahertz or DCS, PCS 1800, 1900 megahertz, and so on. We have a power amplifier here that amplifies the signal when we transmit, and we have an antenna switch because there's only a single antenna, and in this case it's a this is a tri to quad band design here. You see the antenna switch has to switch between 2 different transmit paths depending on the frequency and 3 different receive paths, again depending on the frequency. We have a couple of more signals between them, but that's, if you want to read more about that, I've written a paper on telephone anatomy, and you can read more about the details, how this works together, this entire beast. So, what do we need in order to achieve what we want, the Ethernet card for GSM? We need the baseband chipset under our control, we need the layer 1, we need the layer 2, we need the layer 3. All of them need to be open source, so we can modify them and so on. None of the components existed, so we had to start. There's a couple of different approaches you can do this. One of them is, well, you use documented standard off-the-shelf components and do everything from scratch. So you use a CPU that's publicly available, that's publicly documented. Use a DSP that's publicly documented. You write all the code. Use an FPGA for the synchronous time-controlled signals in GSM. Which means you don't need reverse engineering. You, however, need a lot of work in the hardware and digital logic design and analog design. And in the end, you will end up with something which will be very expensive because it's low quantity. It's a very special purpose device. It's not a neat telephone or something like that. However, as I said, you don't need any secret information. You don't need any reverse engineering. Now, the other option is you can build a board yourself by using existing baseband chipsets. Now, I just previously mentioned that you cannot just go somewhere and buy them. Well, luckily, there is the gray market for semiconductors, where factories in China that didn't actually, I mean, they order 100,000 components and then they only use 90,000. So what do? They do with the remaining 10,000? They put it up for auctions in the gray market. So you can buy lots of components that are not generally available from these gray market traders. That trade in surplus semiconductors. It's an entire industry in itself. Now, and it's quite amazing. I mean, I did this for the Calypso in the beginning when we started, and I put in an interest. You can say, well, I'm interested in this or that component, and I never had that many emails in my inbox ever before on a single day. So hundreds of Chinese companies trying to sell me this chip. For something like, I don't know, $2 each or something, right? It's not that they would earn a lot of money with this, but it works. I wanted 10, by the way, 10. So, yeah, so you can build some hardware, but yeah, it's still custom hardware. You still need, well, you need reverse engineering because, well, you get the chip, but you don't know how it works. And yeah, custom hardware is still low quantity. So the lazy approach that we took, luckily, we found an existing mobile phone that we could repurpose where, well, we know the hardware is working, we know all the analog and digital design is working, otherwise the regular phone wouldn't work. We don't need hardware prototyping, we don't need to do revisions, we don't need to do that much, well, if you can get the schematics with so many phones you can find as part of service manuals and so on, the amount of reverse engineering on the circuit board level is relatively limited. However, still the reverse engineering related to the actual component, the baseband processor and the other peripherals is still there. But in the end, you can focus more of your time to the actual protocol software as opposed to, you know, doing hardware design and, you know, sourcing components and going to a prototype shop and spending a lot of money on. Yeah, and again, you've making a small mistake somewhere. So yeah, by searching for suitable phones, there's a couple of criteria, right? We want a phone that's as cheap as possible because, well, we might break a couple of them in the process. It should be readily available, which means many people can play with it. If you do something like this with a phone where you have the single remaining unit in the market left, then, well, yeah, you can do it and you can be happy that you did it, but where's the point if nobody else can use the result of your work? So you want to use a phone that everyone who's interested in the subject can still buy and can play with the open source software that you create. And of course, you want to use a baseband chipset where a lot of information is known that shouldn't be known. And the result of this was we went for the Texas Instruments Calypso chipset, where the digital baseband documentation interestingly appeared on Cryptome quite a number of years ago already. The analog baseband documentation you can find on Chinese telephone developer websites, which are a very, very useful resource, by the way. Stuff like 52RD, BBS, and other sites are a real fountain of a wealth of information. The source code of a GSM stack that ran on a very strange telephone design based on that chipset was on SourceForge for 4 years. And nobody ever really, TI never took it down. Of course, it was not legitimately on SourceForge, right? So after I made my first presentation, it was taken away from SourceForge, but of course, there are many copies around. The internet doesn't forget. The telephones are end of life. The chipset is end of life, but you can still, until 2008, you could have still bought phones with that chipset. That means only 2 years ago, there are lots of phones that are still somewhere in a stock, or second-hand market is still very large. The other chipset we've started to look at is MediaTek chipsets, where MediaTek is a Taiwanese company that is shipping 95 million baseband chipsets a quarter right now. It's a very high volume. They basically own the low-end GSM phone market today. You can find SDKs, you can find documentation and so on, and that's going to be the next target. But for first target, we chose the TI Calypso because more information was available at that time. We started in January, which is, by the way, 12 months ago, not 9. I should just remove that. We implement the baseband software from scratch. That means protocol stack, hardware drivers. We also want to do some user interface. We don't really have it on the phone yet. However, we have a verbose user interface on the PC that many people will like because it's modeled after a Cisco-style telnet interface. We have, tab completion and everything. So the name, by the way, is Open Source Mobile Communications Baseband. Right, so no questions about that. The software architecture, well, we reuse code from OpenBSC whenever possible. I mean, after all, we already have an open source implementation for the network side of the protocol stack. So we split the generic part into a library called libosmocore, the open source mobile core library, which we use both for the telephone side and for the network side of the GSM stack. And we run as little software as possible in the phone because, well, debugging code on the PC is much easier, right? If you want to do debugging of some embedded stuff running in an ARM microcontroller, JTAG and all that stuff, and you always need to download your new code, and it's just not as convenient as debugging it on the PC, where you can just run it on Valgrind, where you can do whatever you want. You have more screen real estate, right? That's an important factor in debugging something. So what we do now is that of course, the hardware drivers have to run in the phone. We also run the layer 1, which is the time synchronous, very timing critical real-time part of the GSM stack that runs also in the phone. But layers 2 and layer 3 and everything above that so far runs on the PC, which makes, as I said, things much easier for you. Of course, it's written in a way that we can easily move the layer 2 and layer 3 into the phone at some later point when we want to create something that doesn't require a PC attached to the phone all the time. We have a couple of interfaces. There's an interface between the layer 1 on the phone and the layer 2 on the PC. It's called layer 1 control. It's completely custom. There's no specification how to do something like that in the GSM specification. It's a message-based protocol using a HDLC-like layer over RS-232 that goes to the telephone. Then we have the layer 2 code that exposes an interface called RSLMS. If anyone has ever heard of RSL, it's the radio signaling link that's used in the in the radio access network, but the network side of GSM. We modified it to be able to use it on the telephone side as well. It doesn't really fit 100%, but 90% at least. The firmware, so we cross-compile a firmware that contains the layer 1. It contains NOR drivers, LCD drivers, drivers for the hardware, all that. We compile it, we cross-compile it, and we install it onto the actual device. And we will show how that works in just a very short time. There are some, layer 23 is how we call the sum of all the host software programs. That contains, layer 23 is layer 2 and layer 3, and layer 23 is a good number, so that's why it's called layer 23. It uses this layer 1 control API to control the layer 1 on the phone, and it implements, as said, layer 2, layer 3, cell reselection, SIM card. We can access real SIM cards. We can also emulate SIM cards. And we have a support for various apps, and we'll talk about those apps in a minute. Now the hardware, let me just briefly talk about the hardware before we can go into the demo and the actual applications. The hardware that we support, once again, it's the TI Calypso Iota Rita chipset. Well, most people don't know, how can I buy a phone with that chipset? The phones that you can buy are called Motorola C110 something, like 115, 16, 17, 18, 120, 21, 22, 23, and so on and so on. I don't know why they have so many different models. They just differ in the mechanical design or some minor feature here or there, but fundamentally it's all the same. Most of our development and testing is done on the C123 and C155 phones. And by the way, also the GSM modem in the OpenMoco telephones has the same chipset, and somebody has ported it to make work, port. You don't really need to port much, but somebody has made it run also on those phones. If you look at a PCB of such a phone and you remove the shielding covers, it looks a bit like this. You have the actual Calypso, the digital baseband chip down here. It's typically the largest chip in the device. Next to it, we have RAM and flash. This is static RAM, it's SRAM, and it's NOR flash. So there's no NAND flash, no DRAM, no refresh cycles or anything like that. It's all very, low-end deterministic. The CPU doesn't have any caches. The RAM is driven without any wait cycles. You deterministically can tell how long an instruction will take, so you can make sure everything will fit within the tight timing margins of the TDMA system that GSM is. This is the analog baseband chip over here. We have a SIM card socket. This is the transceiver chip that up converts from the baseband into the RF band and down converts. This is the antenna, the RF power amplifier, and left of it the antenna switch module, and this is where the antenna connects to. Also see a battery connector, you see a vibrator connector, you see a headset connector, a buzzer, and so on. This phone does not have a USB interface or anything like that. It's a very, very simple phone. So how do we install code on a telephone? You plug a 2.5 millimeter audio jack into the audio socket, and you download it over RS-232 into the audio socket. That's the official way how all these telephones have been built at that time. It's the official way how they do factory flashing of the software and calibration and so on. It all goes through the earphone jack because, you can't do it over the power jack, can you? The other thing that you have is the earphone jack. So there's actually a GPIO line that you can toggle, and this line determines whether it's analog headset or whether it's digital RS-232 serial line. Now, what do we have working? We have the hardware drivers, we have the layer 1, doing power management, doing carrier synchronization, bit synchronization, TDMA frame synchronization, receive and transmit of bursts, various different bursts. We do automatic gain control, frequency hopping, encryption is not on the slide yet. We have the layer 2, we have the layer 3, and we have cell reselection. So basically, we have a full phone. There are some things that are missing. It can also, of course, do phone calls, right, and SMS. It has full rate and EFR codec, different assignment schemes. We do a SIM card interface, authentication with that. Some things it cannot do. We don't do in-neighbor cell measurements yet, which also means we don't do handover yet. So you cannot really move around using while you have an active call with osmocombb. That's sort of the only practical constraint, the most important practical constraint. We don't have a user interface on the phone, but if somebody wants to do it. There are no circuit switch data calls, there's no GPRS, and of course there's no type approval, but that's not really something we're aiming for anyway. So you can establish control channels and signaling channels and so on to both hopping and non-hopping and encrypted and non-encrypted cells, and you can send them random messages and do whatever you want. We have control over the synthesizer, and this is a regular GSM telephone meant for commercial GSM networks, but because we have control over the synthesizer, we can adjust the frequency and go into the railway GSM network. There's no restriction in the hardware that prevents you from doing so. So you just tune it a couple of, it's actually 2 or 4 megahertz lower than the regular GSM band, and there you go, and you receive DB Systel, Deutsche Bahn here in Berlin. And well, we can send arbitrary messages. We have traffic channel voice calls and so on. Steve will be doing a couple of demos about the various different applications. So maybe we can switch the projector, the input of the projector to Steve's laptop over there, and he will give you a demonstration of the mobile application. This was an instruction to whoever controls the beamer to please switch over. Not sure if there's some magic keyword I need to trigger.
Yeah.
Ah,
Oh, yeah.
okay. Okay, so apparently okay. Steve can go ahead and present on what he can do with the mobile program.
Yeah, so I'll demo the mobile implementation first. First of all, we have an application called osmocomb, which connects to the phone via the serial port, which is already started. Yeah, sure.
This is, by the way, the setup. So we have this 2.5 millimeter audio jack going into the earphone, right? And this is the regular phone. There's no modification has been made to either software or hardware of this phone.
Yeah. So now osmocomb is connected to the serial port and waits for the bootloader command from the phone. And it opens a socket to which higher layer programs like mobile or other applications we'll show in a minute can connect. So now I'll start the mobile application, which connects to the socket. I already can open the VTI.
Here you can see, it still tells you it's the OpenBSC control interface. It's a copy and paste mistake.
Yeah. So now I'll boot up the phone. You can see that the code is downloaded. And there it goes. Now it connects to the network. It just reads the SIM card data and does a power measurement over the whole spectrum.
Yeah, you get the same colorful output as OpenBSC gives you.
But now somehow it loops. Let me check.
So what it does, it cycles over all the different radio frequencies, obtains power measurements to determine where actually a cell is located and where it receives a signal and so on. Hopefully it will find our network that we are running here.
Oh, yeah, that looks good. So, yeah. Yeah, those are very verbose debugging outputs, so these bit errors are nothing uncommon. Yeah, so now we're connected. And yeah, of course, what would you do? Let's try a phone call.
You can call me. You're still on the shell. You have to restart the telnet.
Oh, yeah, sure.
And you can call the 9401 if you want.
What was it? 941?
9401. Say something into the phone.
What did you just say? Test. Test 1, 2. Yeah, it works. Yeah. Yeah. So you can do other stuff as well. There's a help mode integrated in the VTI, so you have a configuration file where you can handcraft and put your own email all the config settings in there. So let me just show it. So here you specify the email. You can emulate all kinds of features. You can say you have no encryption support or no full rate speech support. So you can basically configure your whole phone or let the network believe that you have a 10-year-old mobile phone, for example. So there's a lot of testing that can be done.
Yeah, you can also do things, since we have full control, you can also do things like sort of alter your position as it appears to the mobile network. Because there's this timing advance that is used between the telephone and the BTS, which sort of gives the network an indication how far you are from the BTS. And since we control the timing, of course, we can just adjust our timing a little bit this way or a little bit the other way, and then we appear closer or further apart from the cell, which, well, is an interesting feature, I guess. We can, of course, also combine that by sending handcrafted or modified measurement results, so the network will have an even more complete idea that we are really somewhere else than we claim we are. So,
yeah, one more thing to show maybe is we have fully integrated Wireshark support, so you can use.
I can call you, actually.
Just wait a second. I actually started without the Wireshark support. So there you have it. You see all the system information messages that go from the BTS to the phone and the other way around. Yeah.
Okay, now I'm going to call this phone.
Let's see if it's already completely connected. I'm not sure.
It doesn't.
Now it's completely connected.
I was dialing too soon. Sorry for that.
Yeah, that looks good. Yeah, call is connected. We have auto call.
Yeah. Now, if you can look in the Wireshark, you will see the setup request coming from my telephone number. If you go.
Yeah, let's see where the actual call was established.
Connect a little bit further up here.
Yeah, there's the connect. There was the call alerting, yeah.
Yeah, this is, the ring, when the phone is ringing, you get the alerting message and so on. So, this is the...
Yeah, but you can completely use it for analysis of the GSM traffic.
Okay, let's move to the next app. Can we please switch over to this laptop again for a very short time?
Or if it doesn't work, I have this.
Yeah, you have the slides, so you can. It seems that osmocomb is not the only the only thing where handover is not working yet.
Was it cell lock? Oh, yeah, right. Yeah.
Sorry? Is it mine? Ah, okay. My laptop. Okay, well, okay, I own it. The other application that we have is a cell log application. I'm just going through 2 slides now. The cell log application allows you to scan and log cell beacon information. You can also then send random access channel requests to get the timing advance. So we request a channel from each cell we see, and by establishing a channel for a short time, this timing advance is negotiated, and thereby we also know how far the cell is apart from us, a certain granularity. And then if you connect a GPS receiver, you can obtain you can get all this information, and there's a second program called GSM Map that then parses those logs and uses triangulation to calculate the estimated cell position and generates KML files that you can use with Google Earth. And now, can we please switch over to Steve's laptop again? Thank you.
Yeah, so once again, same procedure, start up the phone. Yeah, now it does the initial power measurement just like mobile did. And now it tries to synchronize to all RCNs found. And there you see, that's the first cell, a T-Mobile cell, and it has a timing advance of 0, which is 0 to 500 meters away. Yeah.
Which is not too surprising, given that we are at a very central location in Berlin.
Sure, and there's our cell, OpenBC. And of course, it has a timing advance of 0. Yeah. So that runs in the loop. You see there are over 500 measurements left, but it creates a log file. Let me just show. Was it there? No. And it saves the system information messages and the reception level of all cells, and of course the timing advance. And then you can feed that into the GSM map application, and you get something like this. So this is the way that was traveled with the phone, yeah, and it calculates with the measurements made the distance and position of the cell. Yeah. Yeah, you can do it in a larger scale as well, for example, yeah. Or even get cells from other countries.
Yeah, this is at the northern coast of Germany, doing some measurements, and you can actually get cells from Denmark, and you get the triangulations into Denmark up there.
About accuracy, let me check. Yeah, it isn't actually that accurate because you have those steps are like in 500 meters, and it's marked there, but it's actually there. So, but it isn't that high difference. Yeah. So, oh no, I don't know. That was not supposed to happen.
Okay,
Yeah.
you can continue with the slides, Steve. I think it's easier that way.
Okay.
I mean, just show the slides. I can do the introductory thing, and
that was the GSM map application. Yeah. So.
Yeah, the other one is actually the first thing, I think, if I remember correctly, was the first thing we had is the BCCH scan application, which is relatively similar. It iterates over the full spectrum, it does a power scan, then it tunes to all the channels that it has a very high received signal strength, acquires the broadcast common control channel and dumps system information and so on to Wireshark. So it's sort of a predecessor of what BCCH log and cell log and so on can do now. I think there's no point in demonstrating it separately, is it? I mean, you've seen that we can send the messages into Wireshark. It's, well...
Basically the same thing, yeah.
Yeah. Okay. Next slide.
Yep.
Yeah, then we have CBCH sniff, which is a cell broadcast channel sniffer that just gets all the data it can get from the cell broadcast channel. Cell broadcast channel is something that used to be used more than it is today. Some operators are actually doing putting their GPS coordinates of the cells in the cell broadcast. I think O2 is the example in Germany here. There are some more apps in there that are mostly R&D related. Well, the idea is that we have this stack now, and we have libraries and interfaces in there that you can use it. So if you want to write a SCAPI fuzzing gateway application that just establishes a radio channel to a cell, and then you can send arbitrary packets from SCAPI, maybe over UDP into this gateway, and then over there, it's all there. The point is that we have those libraries. Go ahead, write your own applications, do interesting things. Okay, so sort of a summary of what has been going on. The GSM industry has been making it very hard to do security analysis, legitimate and non-legitimate. There are well-known security problems in the GSM stacks, both in the implementation as well as in the specification itself. Now we have multiple solutions for sending arbitrary protocol data, both from the network as well as from the telephone. There's OpenBSC, OpenBTS for the network side. There's osmocombb from the baseband side of the telephone. We also have injection proxies, so if you get at one of the other interfaces in the network, in the core network, then you can also inject messages from there. So that's really all there now. Where to go from here? Yeah, as I said, we're still waiting for somebody to do the fuzzing integration. It's up to the security community to make use of this. And I personally think TCP/IP security has been boring for a number of years. There's RFID, there's Tetra, there's GSM, there's 3G, there's DECT. There are all these communication systems out there. Why did nobody ever present here about a GPS transmitter that sends arbitrary satellite information and confuses GPS receivers and so on? There's so many communication systems out there that are waiting for somebody to do practical security analysis. Don't look at TCP/IP all the time. It's boring. It's old. Okay, some thanks, because this really is a group project. We have Dieter Spar, who has been very invaluable to the project. Unfortunately, he was not able to make it to the presentation due to a lot of snow, and he lives in a very remote location. We have Andreas Eversberg, who has been spending most of his summer to implement the layer 3 and the cell reselection and all this. Sylvain Mounon, who has already been on stage yesterday, doing a lot of layer 1 and DSP work. And we have other developers who are working on open source GSM stuff, just to name a few. I really want to thank these guys. They boldly go where no man has gone before. Some links if you want to read more about all this, and now we have 14 minutes for questions. Please raise your hand and go to a microphone and so on. Don't just scream or shout into the hall. Questions?
As for the questions, I want to say that please go to the microphone stands on the left and the right side.
Hey, go to the microphone stands, not outside the door. Thank you.
Yes, there's a question right there.
You mentioned that OpenMoko has the same chip, so since it already has a USB port, how feasible it is to run those tests on it? Have you tried it?
The USB port of any smartphone, including the OpenMoko smartphones, is connected to the application processor, which is a different processor on the same device. So if you want to run osmocombb on the OpenMoko telephone, what you do is you run the layer 2, layer 23, all the applications. You run it on the application processor of the telephone itself, and you run the layer 1 and the firmware that we do for the baseband processor in the processor. So with the OpenMoko phone, you don't need a PC and the phone, but you can run everything inside the phone. But without an external PC, how do you type in the commands to the telnet command line? So you will still somehow need to access it externally.
I have some questions. Hello.
I
have some questions from other missions. One question from Bhutan in England is, would it be possible to create a peer-to-peer GSM network with this modified baseband?
Not really. The fundamental problem that you face is that the uplink and downlink frequencies, which is the frequency from the cell to the phone and from the phone to the cell, they are, depending on the band, between 45 and 90 megahertz apart in frequency. There are hardware filters in the receive and transmit path of the telephone that limit the frequencies you can receive or transmit on. If you do those hardware modifications, so if you do hardware modifications to exchange or replace those filters, then you can turn one telephone permanently into the other way. So it could behave like a cell, but then it could no longer behave like a phone. And aside all of that, you have problems with the timing, because the timing is there's always a clock master. It's a synchronous system. All the telephones are slaves of the clock master, the BTS. So you can probably get a prototype working of 2 telephones or 3 telephones talking to each other, but it's never going to scale and it's never going to work, and especially not without hardware modifications. So I think it's a bad technology for doing that.
Hi. Hypothetically, does the baseband software have to identify itself to the operator? So hypothetically, if you were to talk to a real network, would you have to lie and pretend you were one of the 4 official baseband software or some derivative?
No,
Thank
there's no inquiry, neither authenticated or non-authenticated, onto what particular implementation it is running. It's nothing like that. You indicate the features that you support, like do you support this codec or this cipher, or do you do this, or which band do you support, what's your transmit power, and so on, but it's always on feature base and never on vendor base.
Are operators likely to get annoyed if you were to, or are there any legal implications if you were to hypothetically run this against a real network?
Well, if you hypothetically run it, I think there's no legal implications, but if you really... Sorry. But if you practically run it on a real-world network, which works very well, by the way, I don't really think there are legal... Okay, so you might violate the terms of services of the operator, and if the transmitter, in case the transmitter would not behave according to the regulatory things, regulatory requirements, then you may have some issues there. But even then, unless you actually disrupt communications in a public telephone network, that's sort of, at least according to German law, if you disrupt or interfere with a public communications network, that's subject to up to 5 years of imprisonment. So that's really serious. But just, if it transmits a little bit strangely without causing interference, that's a minor offense, not a big deal. Yes, you might violate the terms of services and the operator may terminate the contract or something, but it's not really a serious issue, at least based on my knowledge about the legal situation here in Germany.
You said about the timing advance, that you can change the timing advance as you like to fake your position. But I remember a lecture from my professors in electric engineering that it's a problem, because if you move it too long, then you will destroy the timing, because you have a distance to the base station, and so the timing advance is to compensate for this distance. And if you move it too long, then you will destroy all the other packets of the other people who have a different distance to the station.
No. The point is not that you transmit. So what we do with the timing advance is that the network tells us, based on your current receive delay, please switch to timing advance 2. But we don't switch to 2, maybe we switch to 3. But we tell the network we switch to 2. So on the air interface, everything is like it's supposed to be, everything is in the time slot it's supposed to be. Just because the network told us something different than we did, there's a wrong assumption of where we are. But there's no interference or anything wrong on the air interface.
What would happen if, for example, you're standing next to the base station and put the maximum value of timing advance?
Well, the point is that we never put the maximum value. We just claim to the network that we are.
Okay, you claim it, okay, but you don't put it, because otherwise you would destroy the packets.
Yeah.
Okay, so what about doing man-in-the-middle attacks? Because you could, for example, take the phone into a base station and take a next phone to be a phone, and then you can, for example, do man-in-the-middle attacks.
That's only possible if you know the problem is there's still the authentication and encryption at that point. And even if you break, you need to break the encryption key fast enough in such a setup. I'm not sure how feasible it is right now, but it's definitely not as easy as some people may think to do the full man in the middle that actually behaves like a proxy. By the way, Rode and Schwarz, a German company of an infamous name, has a patent on this. It's called the virtual BTS, the VBTS, and there's a European patent on the man-in-the-middle attack in GSM networks.
Another question here from somewhere else in the planet. Can one create a GSM server?
There is no terminology in GSM like this. Sorry. I mean, a GSM base station, some people are... a telephone doesn't have the processing capacity that would allow it to run a full base station. Sylvain is doing some work on sort of doing a poor man solution that would allow you to make two phones talk to each other, but it's the processing power of the DSP is not meant to fulfill the requirements of a base station, because a telephone only always transmits and receives on one time slot, because it has one conversation. You don't have 2 or 3 or 4 parallel conversations on a single GSM phone, so you use one time slot. But the base station always needs to provide 8 time slots at least. For all the other telephones and so on. And the CPU, the DSP is just not capable of processing 8 different time slots all the time. So there's some restrictions. Okay.
When I use the osmocombb on a commercial provider network, should I be afraid of disturbing the provider's network in somehow, or is it that stable already so that I'm not afraid to crash the operator's network?
I will not recommend you to do that, no. I mean, it is an experimental project. It's meant for experimentation. We are using this mostly against our own networks. We are also using it, I mean, it also depends on what you do. If you just want to do logging, if you just passively read the system information from the cells, then there's no way you can cause interference. By the way, the default compile configuration of our software disables transmit. So unless you manually edit the makefile and put in some statement that will enable the code for transmit side, it will be receive only, and in that case you cannot cause any interference. So this is a way how you can start to play with. The other thing is, there are operators that are actually interested in testing their networks, and there are some where we've been into the operator lab and be able to use our software against their lab setup. I mean, yes, you can use it in a commercial network, but there's no type of approval, there's no, no legal guarantee, and there's no technical guarantee. I'm fairly confident in the software, but things can always go wrong.
Another question here. How big is the effort to port to other basebands, like GNU Radio or USRP?
That's a completely different architecture than our architecture. The GNU Radio and USRP are software-defined radios where all the signal processing happens in software, whereas the typical GSM design is a much more traditional receiver design. And we are also using for the actual modulation and the modulation is done in hardware. In our case, there's hardware inside the analog baseband that does this. And the demodulation of the signal is done inside the DSP, which has mask ROM code. So the entire receiver architecture is very different. And if you were to, so somebody actually did this. It's not open source, but somebody has taken the OpenBTS code and changed it to no longer be the clock master, the BTS, but to implement the telephone side interface and then put the protocol stack on top of this. You can do it, but you have to know what you're doing. I mean, you need the actual receiver, the signal processing part, in addition to our stack in order to run it on a software-defined radio. And for the signal processing of the telephone side, there's no open source code for that. Also, the USRP costs thousands, well, it's a 4-digit amount of money. The telephones we use, they cost, what, 15 euro, 20 euro? So I would strongly recommend using the telephone. And it has much more output power, right? It can transmit at 2 watts. The USRP only has a couple of 100 milliwatts.
You mentioned you are also able to emulate a SIM card. So if you were to able by accident the SIM card of another subscriber from a mobile and make a call, would the other provider, the other person's SIM card get billed?
The problem with this is that you don't have the encryption key and the authentication key of the other SIM card normally, right? So we can emulate it if you have the key, but since normally you don't have the key, you will not get to this point, unfortunately. There is one exception, though. The session key, as Carsten Nohl has pointed out yesterday, we only have 1 minute left. I have to do this quickly. If the session key lasts typically a couple of sessions, it's not recycled every call or every SMS, depending on the operator. So if you see one transaction and you crack the ciphering key of that transaction, so somebody's making a call, you record that, you crack the key using Kraken and AirProbe and so on, and then you have the TIMSI and the key and all the material you need, and then you contact the network again, and if the network is not configured to do authentication in this case, which a number of commercial networks are, then yes, actually at that point you can make a call, 1 or maybe 2 calls depending on the network configuration from that other subscriber's phone number, and it will be billed to him. But I think it's very, special case and depends a lot on the network configuration. And I think, most operators, if they don't have it yet already now today, it's very easy for them to switch to a configuration that prevents that. Okay, we have 0 seconds left. Well, thank you for your attention, and yeah, have fun.
Thank you.